Hello, my name is Nicolas Cardoso, and today I'm going to present our work on analyzing context-oriented programs with the creation of the points-to analysis. This work was driven by Sergio Cárdenas as part of his master's thesis dissertation in our master program. The work is also developed in collaboration with Paul Leher and Hiroaki Fukuda. The idea of the points-to analysis is to be able to identify the value reference that a pointer or a variable has in the execution of a program. So in this example, in the program on the left, we want to analyze all the values that can be referenced for the f function. As we can see, the values that we can reference are all the objects that are part of the body of the function. So for example, object 1 and object 2 will correspond to the evaluation of the object instances they create. For object 3 to object 6, the result that the function points to depends on the subsequent functions that they are calling. So for example, for object 3, we need to resolve the value for the first function. And in the ideal case, we can resolve this completely based on the specific values of the instances that we're using to call the method. So in this case, we will be using instance 1. We can also repeat this analysis with any other pointer, function, or variable that is available in the program. So for example, the points-to analysis for the first function will have two possible values, the instance 1 and instance 2. This corresponds to the different orderings in which we can call the first function, and those are all the possible values that are reachable for this function. The points-to analysis works well, but it becomes more difficult when we introduce dynamic features into the program. However, these type of features are desirable in our programming language as they helps us deal with the complexity and the changing requirements in the system. For example, by introducing new modularity abstractions that manage this complexity, or by enabling the changing locations of behavior and variables to introduce more flexible and dynamic behavior in the system. One particular way of doing this is using context-oriented programming, a paradigm to enable dynamic adaptations to the context of the execution environment. In context-oriented programming, in this particular example, we are using a messaging object that can send messages. We can adapt the behavior of this message dynamically by first defining the behavioral variation. This behavioral variation, for example, defining an encryption variation in which the send function is annotated with a particular string, should happen only in the presence of a particular context, which we call the encryption context. And we can do this for as many contexts as we like. So here we are using the compression context as another way to annotate the send function for this particular message. However, note that here there is no relation between the message object and the behavioral variations that were defined. To create this relation, we use the adapt construct. This construct associates the context. So in the case of the encryption context, we associate in the encryption object with the message it is adapting and the behavioral variation associated with the context. And the same we can do for the compression context. Now, the final part of the execution of our program is to activate the context. The context activation has an effect on the program so that when we call the send message, the send method on the message object, then we will observe the behavior of the active context. Here, if we activate the encryption context, then the behavior that we will observe is that defined in the left-hand side of the slide. If we then activate the compression context, then we will first observe the send definition defined in the right-hand side of the slide. Note that these definitions use this proceed abstraction, which is also introduced for context-oriented programming to be able to access the behavior from all other adaptations. So when we call send in the compression context, we will proceed to the implementation defined in the encryption context, which will then proceed to use the implementation defined in the base behavior. When we are using context-oriented programming, then calling a message can have different results. and each of the possibilities of the results correspond to a particular definition of a behavioral variation. So in our messaging application example, we will have three possible values for resolving the send function. The function defined in the base behavior, the function defined for the encryption context, and the function defined for the compression context. Taking this into account, our ultimate goal is to be able to define an taking this into account, our end goal is to be able to build an analysis framework to take into account the dynamic and modularity properties of context-oriented programming. And in particular, for this work, we are starting this framework with the definition of a points-to analysis that is precise. To do this, we built a points-to analysis for COP, which first identifies all these adaptive construct abstractions to be able to create a tuple, which is relating the context object, the behavioral variation defined here as a trait, and the object that the adaptation will modify. Having this tuple, then we can transform the program at the AST level by introducing this association between the context and its adaptations and vice versa. Finally, we take this information and use the field-sensitive correlation tracking analysis defined in WALA to be able to calculate the points to set for our context-oriented program. So in the generation of the points to sets, we first identify all the different constructs and abstractions defining context-oriented programming as the ones shown here in the slide. The goal of identifying these abstractions is to be able to modify the AST by providing information about the adaptation and the object in each of the instances of these two concepts. So the first two abstractions, the definition of context and the definition of behavioral variations, actually perceive a very similar adaptation, which is to define the object that they are introducing as part of a property in the program. This adaptation is defining a new property object in the variable that is creating either the context of the behavioral adaptation and associating that with the object. The objective of this is to be able to access this object directly during our analysis. The second construct that we transform is the construct of adapt. Here, we want to introduce an adaptation property to each of the contexts, and we will introduce an adaptation property for each context each time we see a new adapt construct appear in the program. The definition of this property will include the object that the context is modifying and the behavioral variation that we are using to modify that object. And now we will have all the information accessible for the points to analysis. Finally, we work on the activation mechanism for the context. The idea here is to be able to represent what happens to the program when a context is activated. So here we want to be able to use all the properties defined in the context and the behavioral adaptations to map them into the object. So this transformation here highlighted in the code to the right is copying all the properties from one particular behavioral adaptation to the properties of the object that the context is supposed to modify. To be able to do this, then we reuse the association that we transform in the adapt method and the objects that we are creating in the behavioral adaptation and in the context object. Taking all of this information into account, then we define a set of experiments to validate that indeed our points to analysis can capture the dynamicity of context-oriented programming. In our experiments, we implemented 4 different prototypical context-oriented programming application examples taken from the literature In the interest of time, we're only going to show one example here, that one for the shape polymorphism, where a shape can change through the execution of a program. However, very similar results are found in the other applications, and all the results can be found in our online appendix defined that you can find here on the left of the slide. So in the shape application, we have one particular shape with different adaptations, and we want to calculate the points to set for a property within the shape. So for example, here, calculating the points to set for the area function using the field-sensitive analysis of Walla will result in identifying correctly the R1 the R1 value, which corresponds to the implementation of the area function in the shape object. However, this points to set omits all the different adaptations of the area function, which are the ones defined for the triangle behavior and the circle behavior. Note that here in the code, all the different colors encode a different type. So when we calculate the points to set using our approach, then we can correctly identify the results for each of the different adaptations. So here we have R1 representing the result for the base behavior, and R3 and 6 representing the behavior for each of the behavioral adaptations. So the different adaptations of the area method. Similarly, if we calculate the points to set for the number of sites function, we'll have a similar behavior where in the baseline, so in the field sensitive analysis in Walla, we can only identify the result and number 9, which is the definition of the value in the base behavior. But we omit the two other functions, which are reachable from our analysis. Note here that our analysis is already useful to think about the properties of the program, because from the analysis, we can identify that we have different types in the result of one particular function. And this can lead to bugs or errors in the execution of our program, which we can identify using this analysis. However, we want to take the execution of this analysis further. And part of the extensions to our work is to be able to identify the completeness of the program. So our end goal is to be able to say when a particular adaptation can't complete or not its execution. So take, for example, the code here in the slide where we have one object defining a function and two behavioral adaptations associated to that object. Here, if we have, for example, a situation in which we activate context 1 and context 2 and call the bar function on the behavioral adaptation in context 2, then we know that this adaptation is going to finish because the method is calling the base method from the base behavior and the foo method from the context 1 behavior, right? However, if in another situation we only activate context 2, then we know that this activation cannot completely finish when we call the bar function. This is because the foo function is missing as it is not activated in the context. So this is the type of the analysis that we can reach whenever we are extending our points to analysis. To conclude this presentation and thinking about our goal of creating an analysis framework for context-oriented systems, we want to point out that we created the first analysis to capture the dynamic properties and the modularity concerns of context-oriented programming as a base analysis to further reason about this system. Furthermore, our analysis has an improved recall in identifying correctly all possible values pointed by a particular variable or pointer, even in the presence of dynamic adaptations. So if you're interested in our work, feel free to contact us.